Hello, for this problem, we've got a pair of bolt cutters here, and we're asked to find the reaction forces FR1 and FR2. So FR1 and FR2 would be the forces that whatever we're cutting is exerting back on the bolt cutters, and essentially this will be the same thing as the cutting force of our bolt cutters. So with our set of bolt cutters, we've got two blade pieces down here, the top blade and the bottom blade. They're connected. There's a hidden joint back here at point B. And then they're connected by a two-force member connecting points A and C. And then beyond that, we've got two handle pieces that extend out the back. They're connected to the blades and to each other in this center section right here. So we've got a person exerting 150 newtons down like this. We've got a lot of the dimensions, and we're asked to find, we're going to have to go through this particular machine and determine those cutting forces at the end. So since this thing is not independently rigid, we can't treat the whole thing as an extended body. We need to break it down into parts and analyze each of those parts independently. So to start with, we know the forces on this end, so we're going to start with the handles. I've got handle DE and EF, and on this next board right here, I've drawn out kind of a more detailed view of each of those pieces. So DE, we've got 0.21 meters or 21 centimeters from point D horizontally over to our 150 Newton force. We've got vertical distances between E and E and D of 0.2 and 0.04 to get to our 150 newtons right there. And then the angle, this is tilted back at a 20-degree angle between D and E. So to do this, the first thing we need to do is draw in all of the unknown forces. So I've got one of the forces drawn in. I've got my 150 Newton force, and that's acting on the top part here. And I also have an X and a Y force at each one of my pin joints. So I'm going to call this one F dx, F dy, and I've got the same thing at this pin joint here. I'm going to have Fex and Fey. Down here on the bottom, I'm going to do basically the same thing, but there's one important thing to remember, and that is that point E is shared between these two. So I've drawn Ex and Ey in kind of the positive directions here. I need to change that, I need to flip it, and when I draw it down here, I need to draw equal and opposite forces. So Ey is going to be going down, and Ex is going to be going to the left. Fx, I can just draw this one in the regular direction. So Ffy and Ffx over here. And so with that, I've got all of my forces drawn into my free body diagram. I can start drawing out my equilibrium equation. So I'm going to start with the top member up here, so dE, and in the x direction, I'm going to have sum of forces in the x is going to be equal to F dx plus Fex equals 0. In the y direction, I'm going to have F dy plus Fey minus 150 equals 0. Alright, and then I'm going to do sum of moments, and I need to choose a point. So the easiest point to choose right here is going to be point D, since everything is kind of measured from point D. So I'm going to do sum of moments about point D, and that's going to give me three forces that are going to exert a moment. So first I'm going to look at Fex. Fex is going to exert a positive moment, and the distance, the perpendicular distance here is this 0.02 meters. So I'm going to have 0.02 times Fex and that's a positive moment. Fey is also going to exert a positive moment. It's going to cause that counterclockwise rotation. And so the horizontal distance here, if I know my vertical distance is 0.02 and this is a 20-degree angle, I can use the tangent. So I'm going to do 0.02 times the tangent of 20 to find my horizontal distance there. So plus 0.02 times the tangent of 20 times Fey. And then finally I've got my 150 Newton force. So this one's going to exert a negative moment. It would cause a clockwise rotation about point D. And my distance is that 0.21 meters. So minus 0.21 times 150. And so the sum of all those moments is going to be equal to 0. Now I'm going to jump down, and the next thing I need to do is do this is going to be member EF, the bottom member down here. I haven't copied over a lot of the dimensions, but it's basically a mirror image of the top bar there. So in this direction, I'm going to have sum of forces in the x, and that's going to be equal to negative Fex plus Ffx equals 0. Sum of forces in the y, I'm going to have negative Fey, and I'm going to have positive Ffy. And I'm also going to have a positive 150 Newton force down here. All right, and then finally sum of moments. In this case, I'm going to do sum of moments about point F. So sum of moments about point F. And I have very similar things to what I had up here. So sum of moments about F, I'm going to have Fex times 0.02, and that's going to cause counterclockwise rotation, so that's positive 0.02 Fex. The y direction, however, would cause clockwise rotation, so this is actually a negative moment this time. So minus, and my distance again is the same thing I had up here, so 0.02 times the tangent of 20. This is times Fey. And my 150 Newton force, that one's going to cause a counterclockwise rotation. That's going to be a positive moment. So plus, and my distance is going to be 0.21 meters, just like on the top, times 150. All right, so now I've got the equilibrium equations. And before I couldn't solve either one of these independently, because I've got 4 unknowns, and I can only get 3 equations for each of these 2 bodies. But 2 of these unknowns, Fex and Fey, happen on both of them. So all through both of these, I've got 6 unknowns, and I've got 6 total equations here. I won't go into the details of solving this. I'll just kind of skip to solving all this. I used matrix equations to go ahead and solve these equations. So I'm going to get, I've got f dx and f dy. And so f dx ends up being equal to 0. F dy is negative 4,177 newtons. Fex ends up being equal to 0. Fey ends up being equal to 4,327. And Fx is equal to 0, and Fy is equal to positive 4,177 newtons. All right, so down here are the forces that I'm going to look at. And the important ones, Fdy and Fy, are going to be acting on the set of blades that we look at next. So let's go ahead and move on. Next, I'm moving from these two handle pieces in the back, and I'm going to look at the two blades and member AC that's connecting those two blades. So if I draw a free body diagram of those pieces, it'll wind up looking something like this. And so I found already the forces acting at D and F. And so let's look back and see what those were. So the forces at D, in the x direction I had 0, same with F, I had 0 in the x direction. And I had negative 4,177 in Fdy, which means that this force was actually going down. And I've got positive 4,177 at Fy, which means that this one was correct. This one is going up. But it's equal and opposite. So this one, let me redraw this in how it should be. So this one should have been going down. And the x direction basically doesn't exist. That disappears entirely. So these are pushing in, which means, or being pulled in by the blade pieces, which means that they're actually, on our blades, they're going out. So this is Fdy, which was 4,177, like so, and this was Ffy, which is 4,177 newtons, like that. And then the x direction had zeros. So now I need to start drawing in all my unknown forces for this. And I'm looking to get to Fr1 and Fr2. So the first thing I can notice is that this piece right here, this is a two-force member, which means it's in tension or compression. I'm going to assume it is in tension. So I want to have Fc and Fa up here, which means that at this pin joint here and this pin joint here, I only have a force in the y direction. I don't have a force in the x direction because my two-force member. At B, however, I can have Fbx, Fby, and Fby would be going down here. Remember always Newton's third law, they have to be equal and opposite. And I'd have to assume this one is going forward. So, again, we've got a lot of unknowns. We've got 3 different bodies. We can do a lot of different equations. But if we're careful, we can go ahead and figure out the reaction forces with one equation. And that particular equation is going to be the sum of moments. So if we look at this top blade, for the top blade, and I do the sum of moments about point B, I'll notice that Bx and By, they're at that point, so they don't exert a moment. Fa is going down through that point. It doesn't exert a moment. The only things that are going to exert a moment is this known force, 4,177 newtons, and my Fr1 force. So sum of moments about B, I'm going to have 0.07. This is a positive moment from the known force. So 0.07 times 4177 minus my Fr1 force is going to be 0.03 times Fr1 in the negative z direction. So 0.03 times FR1 is equal to 0. And that is an equation I can solve for my FR1 value. So FR1 ends up being equal to 0.07 times 4177 over 0.03. And that gives me the final force, the cutting force from one blade will be equal to 9,746 newtons. All right, so with that, I've got one of the pieces, and if I look down at the bottom, I won't go through the whole thing again, but this is basically a mirror image. If I again do the sum of moments about B, I'm left with only two forces that are going to exert a moment, the known force 4177 and FR2. So FR2 also ends up being equal to 9,746 newtons. So with that, we've gone through and we've gone from our input forces and we've figured out the FR1 and FR2, which is going to be the cutting force from the blade. So really the force that the bolt or whatever we're cutting with this is going to exert back on us. So we've solved our problem. Thank you for watching, and I hope to see you again.